Hi, Mick McQuaid here to welcome you to day 3 of iste798. Today I'd like to talk a little bit about the Internet of Things with the emphasis on the things. So yesterday we talked a little bit about the Internet, and you can't have an Internet of Things without the things, so let's talk about connected things today. And I'm going to follow the book, the Rowland 2015 book, pretty closely here in contrast to yesterday when I went pretty far afield. So you could actually today follow along with the book with this presentation. So without further ado, let's dig into the things part of the Internet of Things. Internet of Things with the emphasis on things. We're going to discuss 4 topics pretty much in the order they come in the Rowland 2015 book, Chapter 2. The types of devices, the device technology, the sensors and actuators, and the issue of powering IoT devices. The issues that we'll talk about today are the differences between specialized and multipurpose devices, the concept of an internet presence without computing power, data gathering from the physical world with sensors and influencing the physical world with actuators, and the role of energy conservation in design constraints. What we're talking about occurs at the edges of the Internet. So recall that a guiding principle of the Internet is that the intelligence be at the edges of the Internet so that simplicity and speed rule in the body of the Internet. So all our attention now is on the edges of the Internet without concern for the devices in the body. The focus of the Internet of Things is on edge devices. Different types of devices are relevant to the Internet, including multipurpose computers, which was the original device connected to the Internet, specialized embedded devices, connected sensors and actuators, and passively trackable objects. And most systems, a complete system, comprises multiple types. For example, a home system might have a smartphone interface, an HVAC, or that's heating, ventilation, and air conditioning controller, remote control door locks, blinds controllers, and motion detection sensors. So all of those together are a system, and there are multiple types of devices. The types of devices are summarized in Table 2-1 in Rowland 2015. And for multipurpose computers, we see that the user interaction offers rich capabilities. The functionality is general purpose, and the processing is powerful onboard processing. For specialized embedded devices, the user interaction is limited and is usually accomplished via web-based or mobile apps. The functionality is highly specialized, and the processing is a combination of very low power onboard processor and cloud services. For connected sensors, the user interaction is usually one way, only via web-based or mobile apps. The functionality is generally single task, and the processing is done mostly in the cloud. And this is true, by the way, I say connected sensors, but this is also true for actuators. For passively trackable objects, the user interaction is one way, and it's only via web-based or mobile apps. And the functionality is just to broadcast the identity of the passively trackable object, and the processing is only done in cloud services. We de-emphasize laptops, tablets, phones, game consoles, set-top boxes, or anything that's typically used as a general-purpose computing device. We use those in Internet of Things as interfaces, but they are not themselves Internet of Things devices. They enable a lot of Internet of Things devices, so we limit our discussion to the extent that we need to talk about enabling IoT rather than IoT itself, for which we're going to really consider those last 3 categories. First, let's talk about embedded devices. So computers are now the cheapest way to do even trivial tasks like timing a toothbrush or regulating the intensity of an air purifier. So specialized computers are installed in washing machines, refrigerators, and so on, along with other technology. Some packaging, such as a car, may include many specialized computers, whereas some packaging, like a washing machine, may include only a single specialized computer. Prior to 2007, i.e. prior to the advent of the iPhone, phones were often classified as embedded devices. But the rise of smartphones in popularity has meant that the most popular phones in developed countries are now general-purpose computers. We face a lot of issues in implementing embedded devices, and these include the presence of harsh operating environments, the need to conserve electricity, the need for error-free operation, the need for automatic failure recovery, and the need for the devices to be maintenance-free. How do we characterize embedded devices? Well, we say that they interact with the physical world. There's an interaction between the digital world and the physical world, both in gathering data and in producing physical actions. And there is the possibility of onboard interaction, although there's also the possibility of remote interaction via the internet. And there is always a direct or indirect internet connection. Embedded hardware usually groups computer parts together on a very simple device called a microcontroller. And this device usually exhibits very low clock speed and very limited RAM compared, say, to a smartphone. And it has a very low electrical power requirement in comparison with, for example, a smartphone. Some of the famous ones include Arduinos, BeagleBones, electric imps, and embeds. Now, the book, here's one point where the book disagrees with me. The book would consider the Raspberry Pi to be an example of embedded hardware. And, you know, I don't think so. It's really a general purpose computer. The reason I think the book characterizes it as embedded hardware is because it's so cheap. It's $35 US dollars in the US. And so that's cheap enough that it can be attached to a lot of devices and is attached to a lot of devices, but it isn't necessarily as cheap as many of the other, and it's certainly not as limited as the other embedded hardware examples. Embedded software characteristics include the need to design it to make the most of very limited resources, and by limited resources I mean the limited resources we just talked about with respect to hardware. So there should be nothing available beyond the immediate task. And it should be stored, the software should be stored in non-volatile memory. And the cheapest non-volatile memory is write once. And more expensive non-volatile memory would allow writing, and so therefore would allow upgrades. And an example of this that's given in the book is that Whirlpool washing machines can be upgraded by attaching a USB drive with new firmware. And speaking of firmware, there's specialist operating system, if any. There's rarely a general operating system. Connected sensors constitute a special class of embedded device. They have enough onboard computing power to gather and transmit data, but usually no onboard user input or output capabilities, which means there are no displays, no buttons, no knobs. They're completely dependent on other devices for input-output. They have a low profile. They're generally not noticed by end users. And they're often deployed as sensor networks where you have a whole bunch of connected sensors working together. So here are some examples of sensor networks. You could have thousands of air quality sensors across a metropolitan area. You could have dozens of motion contact sensors for building security. You could have a Proteus pill that you take. This is a pill that you take that once it's in your stomach interacts with stomach acid and signals a Bluetooth skin patch, which in turn signals a mobile phone, which in turn sends a signal to your doctor on the internet so that it's clear that you haven't forgotten to take your pill. And as the network grows, it becomes more resistant to the failure of individual sensors. So you can imagine that the thousands of air quality sensors is much more resistant to failure than the dozens of motion contact sensors. And then that again is more resistant to failure than the individual Proteus pill with its Bluetooth skin patch and phone. The next category for our concern is passively trackable objects. So these could include RFID tags, of which there are read-only RFID tags such as PET ID devices, which are about twice the size of a rice grain, and I mean like twice the size of a short grain rice. RFID tags that are read-write, which are typically a bit larger and a little bit more power hungry, which allow direct updates and therefore some kind of interaction. QR codes. So an example that Rowland gives is each bottle of whiskey is produced with a QR code on it, and you can record a gift, a greeting, some kind of a video for the recipient, and then the recipient uses the QR code to visit the video that you've recorded. So that's an example of a use of QR codes, and of course there are vastly many QR codes generally encode a URL and potentially some instructions in the URL. Near field computing or near field communication, I forget now what NFC stands for, but the important thing about NFC is that it uses a single common format called NDEF. So this makes it well suited to things like payment processing. So a lot of phones, for example, now are equipped with NFC for payment processing. Beacons. So an example is iBeacon that uses Bluetooth low energy to broadcast usually an identifier, or in the case of the physical web project, to broadcast a URL. Sensors and actuators bridge physical and digital worlds. Sensors interpret physical phenomena as numeric values for digital transmission. Actuators convert digital instructions into mechanical actions. So together, sensors and actuators provide a complete round-trip interaction with the environment. A sensor may be passive or active. For example, a passive motion detector interprets infrared radiation from humans. An active motion detector, on the other hand, projects beams which, when broken, indicate motion. So any kind of sensor could be passive or active. Sensors take a wide range of inputs, from motion to light to air quality, for example, via conductivity of chemical reactions with a sensor, physical contact, location via GPS, proximity via signal strength, humidity, orientation via magnetic fields, or acceleration via vibration or gyroscope. Actuators convert electrical energy into mechanical energy. They can control valves or control mechanical switches, for instance. And they can even control bubble-blowing machines. The book gives a hilarious example of a machine that blows a bubble whenever a tweet mentions a given hashtag, which is user configurable. A big issue, maybe the biggest, is electrical power. So many devices use batteries for portability, for the simplicity of installation, because of the absence of mains power, which in the US we call household power, and in places where it's just unsafe to use mains power, for example, in a gas meter. And batteries need charging, so batteries can be charged in many conventional ways. Also, increasingly, they're being charged by wind, solar, or even kinetic energy. So there are designs for IoT devices have power conservation as a paramount constraint, and they do lots of different things to conserve power, such as having a sleep mode, doing as little processing as possible, avoiding direct connections to the internet, or avoiding a constant connection to the internet, and designing of interactions asynchronously so that we don't expect a response immediately to an action. Okay, that's a wrap for the things part of the Internet of Things. Thank you very much for your attention, and I look forward to speaking to you again tomorrow.